Now finally, we come to the final topics. Heat treatment for non-ferrous alloy. That would be for aluminum, copper, magnesium, and so on. And to this review, I'll be talking about aluminum alloys. And the main heat treatment for non-ferrous alloy, we have the precipitation hardening, and we also call it age hardening as well. So what we need is the phase diagram. So you have to recall the phase diagram every time you're doing heat treatment. It's something that you can't avoid. Now I'm starting to draw. If you may recognize the eutectic system. Okay, for example, we're starting with aluminum with the addition of copper in weight percent to the right hand side. So up here is the temperature. For the for the eutectic binary phase diagram, we start with liquid over here, liquidus line, solidus line, and also solubility line or solvus line. That is very important. That is the first start when we talk about precipitation hardening. Over here is the alpha solid solution. So right here, alpha plus liquid, and down here is the two-phase region, alpha plus the other phase over here. So right here we have the theta phase, that is the copper aluminide, which is the intermetallic compounds. Right, to this, the first thing is, and the most important thing is this line. That is the solvus line. Okay, and this is the solubility line. If you remember that, by heating up the composition for the start, if we starting with, for example, 4% of copper, if we heat up, passing through the solubility line, entering in the single phase region of solid solution, we now having just one phase. So at this point, such as point A, what we have here is just the alpha solid solution phase, isn't it? So for precipitation hardening, there are requirements. The first one, you have to have reducing solubility with decreasing temperature. Otherwise, you can't get into precipitation hardening. That's the first requirement. So let me carry on. When we entering the solvus line, crossing the solvus line into the single phase of alpha solid solution, we arrive at this alpha phase, right? If we cool down, for example, to point B, maybe at room temperature, for example, we're crossing the solvus line, entering the two-phase region. So if we arrive at B by slow cooling, let's say we get into the equilibrium condition. Now in equilibrium at point B, we can't have just the alpha phase, can we? What we have now is the theta phase, or the second phase precipitates out. So we have the phase consists of alpha solid solution and the theta phase over here. But in equilibrium, the theta phase or precipitate phase are quite coarse and also non-coherent to the matrix. That means it can't resist the deformation applied by external forces. It can't contribute to stress or hardness. So we have to change. We don't want coarse theta precipitate phase. We have to change. But we're not applying slow cooling, but if we apply fast cooling from A to B, if we arrive at B by quenching, so I introduced you here again the quenching. That means very rapid cooling by putting the sample from the furnace into water. That is water quenching. By this rapid cooling, what we have here is also the alpha phase. But this alpha phase has a lot or too much of the copper into the single solid solution. You remember, at high temperature, alpha phase can dissolve high amount of copper, but at lower temperature, the solubility reduces. But when we quench the alpha phase down to room temperature, it's like we force the copper to dissolve into the single solid solution. Now we have SSSS, or the super saturated solid solution. It means that you have too much of copper dissolved into the alpha phase. That's you forcing it. It's like you're eating too much. It's not stable, isn't it? So what will happen to the metastable phase? Start to change back into equilibrium, isn't it? It's like when you eat too much, you need to throw up, and that's the same. After quenching for a certain period of time, we go to the process called aging. And aging can be done at high temp or room temperature. This is the difference, because when you involve high temperature, you have the atom moving faster, so you arrive at the peak hardness quicker. And for high temperature aging, we called artificial aging. And if we age at room temperature, we call it natural aging. Okay, if I explain this microstructure changes, the last one now, when we enter the aging condition, previously we have the alpha phase that has too much amount of copper dissolved into its structure. By aging, increasing time will allow the copper to form the precipitate phase, and the precipitate phase is now very fine. Very fine. precipitate phase of the zeta phase. And this very fine precipitate phase is also coherent with the matrix. So it contributes to hardness and strength very, very well. So this is the situation that we want for precipitation hardening by the fine precipitate phase that coherent with the matrix. And the matrix is the alpha phase. Right, if I come back to draw the heat treatment schedule, that we start with temperature on the y-axis and time on the x-axis. To this, what we have to do, if we start at 4% of copper, we heat up to arrive at alpha solid solution, right? Therefore, the first step is always heating up to a level of temperature over here. We call this solution treatment. And if you recognize solution, it means that we make the metal alloy into solution. It's the solid solution. That is called solution treatment. Okay, and the temperature required for solution treatment is around the eutectic temperature. Remember, eutectic temperature. And for this aluminum copper, your eutectic temperature is around 548 Celsius. So you heat up around this temperature, let's say 550. Then we have to quench it down, not cooling slowly. When we apply quenching, we have the steep curve over here. Maybe water, quenching. Right. Now when we cool the metal rapidly, it will give you the metastable phase of supersaturated solid solution, and now with time we change into the equilibrium phase by precipitate out the refined phase. Then we have to help it a little bit with high temperature aging. For the fourth step, we entering aging at high temperature. It is the artificial aging, and then cooling. If we do it at room temperature, so we apply the natural aging, and that will need more time to obtain the hardness. Okay, so this is the heat treatment for non-ferrous alloys, either aluminum, copper, or magnesium alloys. Oh, one thing that I haven't mentioned about is the second requirement. This is very important because the first thing that we have to consider about precipitation hardening, that we have to have the reducing solubility line with decreasing temperature in this alloy system. And the second thing is that you have to have coherency between the precipitate and the matrix. Otherwise, it can't contribute. The precipitate will not contribute to increasing hardness or strength. Okay, let's see the last thing that we will discuss. I will relate the properties of the alloys to the heat treatment. so you know how important it is. And the heat treatment is for the non-ferrous alloys. So we're aiming for having a greater hardness and strength for non-ferrous alloy. And for aluminum in particular, aluminum normally has a lower hardness and lower strength in comparison to the steel. And what we need to do is to improve the strength and hardness to aluminum, because it has very good advantages of being lighter. Okay, so if we have lighter materials, lighter metals, and with good strength, why not using it by replacing the steel? Right, that is for material selection. And if I start with this relationship between aging time on the x-axis, and the y-axis would be property such as yield strength, tensile strength, or even hardness. And when we do aging, we may apply the aging time from 2 hours up to 24 hours. Okay, and the hardness or strength will develop through the aging time until reaching the peak hardness, and then goes down. So what we need here is the peak hardness, and we have to find out what kind of temperature and time required to have peak hardness. Okay, this is what we have to find out. And if we do the aging at a fixed temperature, okay, the hardness will increase to the top and then goes down. And to this, because of the phase evolution during aging. Okay, and that I will draw some microstructure. When we start at the 0 time, mean we just get the alloy after quenching. After quenching, we have supersaturated solid solution in the first step. Okay, when we look at the microstructure, we have just the alpha phase that has been dissolved, that have very high amount of copper dissolved into it. That's why we have supersaturated solid solution is the metastable phase. But with increasing aging time, the copper in the structure in the lattice diffused to get together, and that will form the so-called GP zone. In the GP zone, the microstructure change a little, that we also have the alpha phase as the matrix. And as the copper atoms diffuse to get together, it will form the feature called GP zone. But the GP zone do not have exact micro composition. It's very small. So this very fine precipitate is still in the stage of under aging. That means it can't contribute to the peak hardness just yet, but with time this precipitate phase that is very small will grow until reaching the optimum size. So with time, until reaching theta prime and theta phase. Okay, as I write down over here, these two phases are not the equilibrium phase, which is down here. As you remember on the last slide, the equilibrium phase of zeta phase is very close and not coherent to the matrix. So what we need is the zeta double prime and the zeta prime. With increasing aging time, the microstructure now we have the alpha and also the optimum size of the zeta phase. So when we arrive at optimum size of zeta phase, we have good coherency between the zeta phase and the matrix that contribute to the peak hardness and the peak strength. And this is the condition that we can obtain peak hardness at the suitable time over here. Okay, but if we do the aging further, the zeta prime entering the equilibrium phase, that the precipitate goes too big now. So when we increase the aging time further, we now arrive at the equilibrium condition that the zeta phase grows too big. As we can see over here, when it grows too big, the phase is too coarse and non-coherent. This is not contributing to the peak hardness. So now we are arriving at over 18 that we don't want it. Okay, so finally what I would like to wrap up is for the engineer to find suitable temperature and time to achieve the so-called peak hardness